Okay, so in this video, we are going to be looking at the applications of the ideal gas law. And so before we get into the calculations, we need to talk about what constitutes an ideal gas. So in order to be considered an ideal gas, 5 conditions have to be met under the conditions of pressure and temperature that we find the gas in. So the first one is all particles have to be in constant random motion, meaning that the molecules of the gas or the atoms of the gas have to be moving at random without stopping. Okay, which seems pretty easy for a gas, given what we know of gas properties. All right. Number 2, the collisions have to be perfectly elastic. So when the molecules collide, they have to enter and exit the collision with the same amount of energy. So no energy is lost or gained as the molecules collide. All right, the third one, the volume of the gas particles in the sample is negligible. Okay, so think about this one a little bit more in depth. So we normally consider volume of a gas to be the volume of the container because the gas is going to fill the container completely. What this is actually saying, it's not the volume of the container, it's the particles of gas themselves. So if you think about gas as little circles, right? This is the volume of the circle, the volume of the molecule itself. So when you have your particles, when you have your gas molecules spread out over a far distance, the volume of one particular molecule or one particular atom is rather irrelevant because in comparison to the larger space, it's just so tiny, it's negligible. But consider what happens if I were to take, for example, my classroom's worth of gas and put it under high pressure scenario and compress it into a small box, right? So I'm forcing all of those molecules together into this really tight location. Well, at that point, when they're pretty close together, the actual volume of the circular particle, if that's how you're conceptualizing this, is going to start to matter, is going to start to have an effect on overall volume. Okay. Average kinetic energy is equal to the Kelvin temperature. So the higher the temperature, the more the molecules move. The lower the temperature, the less the molecules move. And then finally, the gas particles do not attract one another, meaning that there are no intermolecular forces. And so in order to be considered ideal, you have to meet all 5 of those simultaneously. And it's possible for what we would consider a real gas to meet all of those. But if you change the environmental conditions, that's going to start to be an issue, specifically with 3 and 5. There's no such thing as an ideal gas, but most real gases will behave ideally until exposed to 2 extremes of environmental conditions. The first one would be high pressure, and the second one would be low temperature. So as pressure increases and temperature decreases, think about the fact that your molecules slow down and condense. They get close together. And when they get close together and they slow down, we are going to see extreme violation of 3 and 5. When they are put into high pressure and forced together, the volume of the individual gas particles is for sure going to start to have an effect. You can't just ignore that volume when it's starting to condense. And then as temperature decreases, your molecules are going to slow down. And as they slow down, they do start to demonstrate intermolecular attraction. So for example, if you were to consider a sample of chlorine gas, right? If I have a large sample of chlorine gas and my particles are moving fast and spread out, the chlorine molecules aren't going to form any of those London dispersion forces. They're zooming past each other way too fast. But if you slow them down and they start to pass each other at a slower clip, the chance of them making those instantaneous intermolecular attractions as they go by increases. So increasing the pressure and decreasing the temperature is going to cause us to violate the 5 parts of what's called the kinetic molecular theory that governs ideal gases. But whether or not we have actual ideal gases. The fact that real gases behave ideally under most conditions allows us to take advantage of what's called the ideal gas equation, which is PV equals nRT. And we have discussed some of these variables in our combined gas law video that we looked at the other day. P is pressure, V is volume, N is the number of moles, R is our universal gas constant, and T is temperature. So let's break down kind of the requirements of each of those measurements. So P is pressure. That pressure can be atmospheres, it can be torr, it can be millimeters of mercury, it can be kPa. Any of those standard pressure units would be applicable here as well. Volume. Volume here is going to have to be in liters. Milliliters is not going to be an option for the ideal gas law. The reason it's going to have to be in liters comes down to the gas constant R and the units that R brings with it to the table. So we'll see that here in just a second. But suffice it to say, volume must be period in liters, period. N is the number of moles. So if you are given grams, if you are given formula units, if you are given molecules, if you're given atoms, you're going to have to do those stoichiometric conversions to get to moles in order to plug into the ideal gas equation. R is the gas constant. So depending on the pressure unit that you are in, you're going to have a different gas constant. In fact, it's very, very important that the unit that you have for pressure and the pressure unit of the gas constant match. If you don't have them match, you won't be in for a real hard time. So let's look at our gas constants. All right, so there are 3 gas constants on our reference packet, and they're found right below Avogadro's number in that first table. So the first one, 0.0821 liters times atmospheres over moles times Kelvin. The second one, 62.4 liters times millimeters of mercury over moles times Kelvin. And then the bottom one, 8.314 liters times kPa over moles times Kelvin. So you should notice a couple things. First, the liters, the moles, and the Kelvin are consistent, which should again explain why my volume has to be in liters. And as we've previously discussed, anytime you're doing gas law problems, temperature has to be in Kelvin. The liters and the Kelvin aren't going to cancel out appropriately if they are not in matching units. So milliliters won't work, it's got to be in liters. Celsius won't work, it's got to be in Kelvin. Same thing with the moles. It's going to have to be in moles. It can't be in grams. It's not going to cancel right. And then notice what's different. In addition to the numerical values being different, it's the pressure units that makes a difference here. So I need to make sure that if my pressure is in atmospheres, I'm using the R for atmospheres. If my pressure is in millimeters of mercury, I'm using the R for millimeters of mercury, and same thing for kPa. And then also note that there is not a pressure or a gas constant for pounds to square inch. So I can't use that one in an ideal gas equation. I would have to convert to one of these 3. And there's also not one for pascals. I'd have to convert from pascals to kilopascals. So I'm limited to what these 3 are in terms of calculating. And then again, temperature. Oops, I got to zoom back out. Temperature has to be in Kelvin. All right. So a couple important conversion factors that will be helpful. Again, it's always worth remembering. 1,000 milliliters is equivalent to 1 liter. And to get from Celsius to Kelvin, you add 273. One last note before we start calculating. If you're asked to solve for pressure and a particular unit is not specified, always go to atmospheres. That is kind of the standard jumping off point. So if it says, what's the pressure of, and then they give you all of the other variables, but it doesn't say do it in kPa or do it in millimeters mercury, always just default to atmospheres. All right, so we're going to do 4 examples of calculating with the ideal gas law, and that should be enough to get you through for your assignment. All right, so the first one, what volume would be occupied by 150 grams of oxygen gas, O2, at 2.50 atmospheres and 25 degrees Celsius? So just like we did the other day with our combined gas law, I find that it's very helpful to make a list. There are significantly fewer variables than what we saw with the combined gas law, but there's a lot more likelihood here that you'd have to do some pre-conversions before plugging in. And it just makes it easier to see it, for it to be right in front of you, so that way you don't accidentally start plugging in without doing the appropriate conversions. So I'm going to go right through my problem just like we did the other day. I'm going to identify my variables. I'm going to put them in my list. I'm going to see what I have left. So number one, what volume? Well, that means I'm solving for volume. So volume is my question mark. Would be occupied by 150 grams. Well, there's nowhere here that I need grams, but I know I need moles, and I know I can use grams to get to moles. So I'm going to fill in my grams in my mole spot as a placeholder, and then I'm going to do that conversion. At 2.50 atmospheres, that's my pressure, and 25 degrees Celsius, that is my temperature. All right, so pressure, volume is what I'm looking for. This will get me moles. What is my R? Remember that my R units and my pressure units have to match. So if my pressure is in atmospheres, I need to go to the reference packet and I need to choose the pressure unit that is likewise in atmospheres. So my atmospheres pressure unit is 0.0821. So 0.0821, and that's liters times atmospheres, moles times Kelvin. All right. And now I need to go ahead and do some conversions. I know that I need moles. I currently have grams, so I know how to convert from grams to moles. 1 mole O2 over 32.00 grams O2. So I'm going to calculate that out. I'm not going to write down all the decimal places, but I am going to hold that number, that value in my calculator if it is a long, long decimal. This one just happens to not be super long, so I'll write them all down. So there's my moles. And then 25 degrees Celsius plus 273 is going to give me 298 Kelvin. So now that I have all the appropriate units, I need to look at my formula and then rearrange my formula. So I always start with PV equals nRT. And this time I'm solving for volume. So if I want to isolate the volume, I'm going to divide by the pressure to get that to go to the other side. And now I can solve for volume. So V is going to be equal to the moles, 4.6875 moles, times 0.0821 liters, atmospheres, moles, Kelvin, times 298 Kelvin over, what was my pressure? 2.50 atmosphere. And you don't have to write all those units down in your work. I'm just showing you for this first one that everything does in fact cancel. So my moles and my moles cancel out. My Kelvin and my Kelvin cancels out. My atmosphere and my atmospheres cancel out. It's going to leave me in liters, which, because I'm solving for volume, is pretty fortunate. All right, so 4.6875 times 0.0821 times 298 divided by 2.50. And that's going to give me 45.87. And I'm going to look at my original sig figs. Looks like the smallest initial number of sig figs is 25. And so volume is going to be equal to 2 sig figs, 46 liters. And I do have a substance here, so I'm going to fill in the substance O2. All right. It's plug and chug math. The math itself is not hard. You just have to make sure you're making the appropriate conversions first. All right, let's look at our second example. What is the pressure in kPa? So you're getting specifically, it's asked for in kPa, of a 105 gram N2 sample in 45 milliliter container at standard temperature. So P, V, N, R, and T. All right, so let's go through and fill in our variables. What is the pressure in kPa? So I don't know what the number is yet, but I know what the desired unit is going to be. So the pressure in kPa, if 105 grams of N2, so 105 grams of N2 is going to be where I'm going to get my moles from, in a 45 milliliter, that's my volume, going to have to convert that as well, container at standard temperature. Well, standard temperature in words is telling me that my temperature is 273 Kelvin. Remember, that is my standard temperature. All right, and R. Well, if my pressure is going to come out in kPa, I need my R for kPa. So go to the reference packet, I look up the R for kPa, and it is 8.314 liters kPa moles Kelvin. All right, so I'm going to have to do some conversions here. The first one, to get from my milliliters to liters, I know that 1 liter is equivalent to 1,000 milliliters. My milliliters are going to cancel and leave me in liters. So moving my decimal 3 places to the left, 0.045 liters. Okay, then I've got my grams. I need to go to moles. 1 mole N2 over 28.02 grams N2, and that time it does give me kind of a long number, so I'm just going to write down the beginning of it and keep the rest of it in my calculator, 3.747 and change. And everything else looks good, no other conversions required. So PV equals nRT. I'm solving for pressure, so that means I'm going to divide by my volume to move my volume to the other side. So P equals the N, 3.747, remember I'm using the whole number from the calculator, times 8.314 times 273 divided by my volume, 0.045. All right, and then calculating, I already have my moles in the calculator, so times 8.314 times 273 divided by 0.045, and that gets me a pressure of 189,008. Okay, sig figs. Looks like I can keep 2, so 190,000 kPa, and our substance is N2. So that's the specific pressure of the N2. Okay. All right, so we got 2 more. A sample of hydrogen gas has a volume of 8.56 liters at 273 Kelvin and 1.5 atmosphere. How many grams does the sample contain? All right, so let's make our list. P, V, N, R, and T. A sample of gas has a volume of 8.56 liters at 273 Kelvin and 1.5 atmospheres. How many grams? Well, where do I get grams from? I'm going to get grams from moles. So I'm really solving for moles and then converting to grams. All right, the last missing piece is my R, pressures in atmospheres. So I need to use the atmosphere R, which is 0.0821 liters atmosphere, mole, Kelvin. Everything is in the appropriate unit. I don't need to convert anything ahead of time today or with this one. PV equals nRT. Going to solve for moles by dividing PV by RT, and that's going to get N by itself. So pressure, 1.5 times the volume, 8.56, divided by 0.0821 times 273. So remember, when I'm solving for that, that's going to give me the moles. And the question doesn't want moles. My question wants grams, but I'm going to have to use that mole number in order to convert to the grams. So when I calculate this, I get, a mole value of 0.5729287. I'm going to use the whole number in the calculator and change. But I want it in grams. And so this is hydrogen gas. So I'm going to convert these moles to grams by multiplying by the molar mass. 2.016 grams H2 over 1 mole H2. And so when I multiply that by 2.016, it gives me 1.154 to 2 sig figs is going to be 1.2 grams H2. So even though moles don't appear in my formula, I know that even though grams don't appear in my formula, I know moles do. And if I can get moles, I can get grams. All right. All right, our last one At what temperature will 0.35 moles of CO2 occupy 6.3 liters at 1 atmosphere? Oh, okay, seems pretty straightforward. P, V, N, R, T. So at what temperature, I'm solving for T, will 0.35 moles of CO2 occupy 6.3 liters at 1.0 atm. So 1 atmosphere, I need to use the atmosphere R, 0.0821. Go to my equation, PV equals nRT. I'm solving for T, so I'm going to divide this side by nR and plug in 1.0 times 6.3 over 0.35 times 0.0821. And 6.3, I don't need to multiply by 1, divided by 0.35 times 0.0821. 219 and change. When I look at my sig figs, looks like 2. So 220, and remember, this does come out as Kelvin. So the question did not specify Celsius or Kelvin, so I'm going to leave it. If it did specify Celsius, remember that I would just take my Kelvin number pre-sig figging, subtract the 273. In this case, we'd get a negative number. So that's pretty much it for for ideal gas law. Just make sure you watch your units. Has to be in liters, has to be in moles, has to be in Kelvin. Okay.